Welcome students, myself G B Patel, lecturer in Mechanical Department VPMP Polytechnic. The subject is Fluid Mechanics and Hydraulic Machine. The subject code is 3331903. Today we are going to discuss the specific speed of pump. The objective of this video is to derive the specific speed of pump. Let us understand the specific speed of pump, which is denoted by NS. Take one actual centrifugal pump which operates against a unit head operate against a head H, which is in meter, which discharge is Q. The discharge is measured in meter cube per second. Its speed is n rpm, capital N rpm. Okay, take one design model centrifugal pump which operates against a unit head. Unit head means H is equal to 1 meter cube, which delivered 1 unit discharge. That means Q is equal to 1 meter cube per second. This design model centrifugal pump is geometrical similar with actual centrifugal pump. Geometrical similar means a model design pump is similar or identical in shape with actual centrifugal pump, and geometrical dimension like gate opening, diffuser angle, vane angle, etc., blade angle, etc. Then the speed of this turbine, geometrical similar turbine, is considered as specific speed of pump. Let us read the definition. It is defined as the speed of geometrical similar pump. This is geometrical similar design model pump, which will deliver unit discharge 1 meter cube per second against a unit head H is equal to 1 unit. Let us derive the specific speed of pump. Tangential velocity of pump is denoted by small u, and that small u can be calculated by this equation. A small u is equal to PdN divided by 60. This d is diameter of the pump, n rpm speed of the pump, pi by 60 is constant. In this equation, pi by 60 is constant. That is why we can say u is directly proportional to diameter and speed. Multiplication of diameter and speed dn. So u is directly proportional to d into n. Say equation number 1. As we know, the tangential velocity u is directly proportional to flow velocity vf. Okay, so u is directly proportional to flow velocity vf, flow velocity of water. So u is directly proportional to vf, and we know vf is equal to square root 2gh. So square root 2gh, in this equation square root 2g is constant, so we can say vf is directly proportional to square root h. So vf is directly proportional to square root h. So we can say u is directly proportional to vf and directly proportional to square root h. Substituting the equation 2, value of equation 2 in equation 1. So u is directly proportional to square root h. So in this equation number 1, instead of u we can put square root h. So we can get, instead of u we can put square root h. So square root h directly proportional to d into n. This equation square root h is directly proportional to d into n. That is why d is equal to d is directly proportional to square root h divided by n. Say equation number 3. Now discharge q is equal to velocity into area. So this area can be calculated by this equation pi by 4 d square. So q is equal to vf as it is. Instead of this area we can put pi by 4 d square. So in this equation pi by 4 is constant. So we can say q is directly proportional to d square. Q is directly proportional to Vf into d square because pi by 4 is a constant. So we can say Q is directly proportional to Vf into d square. Now Vf is directly proportional to square root h, equation number 2. You can see here Vf is directly proportional to square root h. So instead of Vf, we can put square root h. So Q is directly proportional to, instead of Vf, we are putting square root h into d square. So Q is directly proportional to square root h. Instead of d, I can put square root h divided by n, equation number 3. Instead of d, you can put square root h divided by n. So here, instead of d, I can put here square root h divided by n, a whole square. That is why Q is directly proportional to square root h. Square root and square get cancelled, so it's h only. And here n raised to 2, so it's n square. So here h raised to 1 half, h raised to 1, base is same. So we have to make the summation of index. So 1 plus 1 half is equal to 3 by 2. So here h raised to 3 by 2 divided by n square. Now n square, that is directly proportional to h raised to 3 by 2 divided by q. Take a square root on both sides. So I can get n directly proportional to h raised to square root of 3 by 2 is 3 by 4. So h raised to 3 by 4 and square root q. So here I put square root q. To remove this proportionality, I have to put a k. So n is equal to k, h raised to 3 by 4 divided by q, where k is constant. For specific speed of pump, q must be 1, h must be 1, and n must be ns. See the slide number 1. Yes. For the specific speed of a geometrical similar pump, discharge q must be 1 meter cube per second and h must be 1 meter. Then n become the ns. So for specific speed, I put q is equal to 1 and h is equal to 1, n is equal to ns in equation number 4 in this equation. Okay, so n is equal to ns, h is equal to 1, q is equal to 1. So I can get here n, instead of n I can put here ns, k as it is, h is equal to 1, q is equal to 1. So I can get ns is equal to k. So put this value of k in equation 4, in this equation here ns. So I can get n is equal to ns into h raised to 3 by 4 divided by square root q. That's why ns is equal to, take square root q on the left hand side, h raised to 3 by 4 on the left hand side. So I can get ns is equal to n square root q divided by h raised to 3 by 4. Here ns is a specific speed of geometrical similar pump, n is speed of actual pump, q is discharge of actual pump, h is head against which actual pump is run. Okay, so this is the final equation of the specific speed. Okay, thank you very much.